Hey, I'm Tinos, and I'm making an open source robot arm. In this video, we're finding out what motors to use by pushing them to their limits. As a reminder from the last video, brushless motors are all pretty much the same internally. There's a rotating ring that's lined with magnets, and there's a steel core wrapped with copper windings that generate a magnetic field. For this robot arm, short motors with a large diameter are better than taller motors with the same diameter, because they generate a lot more torque. In this video, I'll be testing every single one of these motors to figure out exactly how much torque they can make, and in the next video I'll be using that data to decide what motor and gearbox size to pick for each robot joint. For a given robot joint, using a motor with more torque means that we can use a lower ratio gearbox, and that means less friction. The sweet spot for gearbox ratios is at about 20:1 ratios or lower. That's called a quasi-direct drive actuator. Since I'm going to be running a lot of tests on these motors, I'd like the setup to be exactly the same between them, so I'm only measuring the variables that I really care about. The test jig has to hold the motor and the motor controller in place, and should be able to handle relatively high forces without bending. I'm using 2020 aluminum extrusion for the base because it's highly adjustable. There's two different sheet metal brackets with different hole patterns to accommodate all 6 of the motors we're going to be testing. And there's another small bracket to hold the motor controller parallel to the back of the motors. These two metal brackets sandwich a 3D printed part that spaces them correctly and attaches directly to the aluminum extrusion base. This gap is needed because I have to attach a magnet to the back of each motor so that the motor controller can properly sense the angle of the rotor. I modeled each of the configurations in Onshape to make sure everything would fit, and then I ordered the sheet metal parts and got to printing. Since I was already placing a sheet metal order, I also modeled a few different gearbox sizes and designed brackets for them to perform actuator testing, which I'll cover in the next video. After a quick fit check to make sure that the stack-up was correct, I started crimping some temperature sensors and soldering connectors to each motor to make swapping them out a lot easier. Finally, after hours of crimping, soldering, and assembling, the design I had stared at on my computer for the past couple of weeks slowly became a functional test jig on my workbench. So let's talk about what we're actually testing. For this testing that we're doing, there's two concepts that are really important to understand, and those are a motor's torque constant and thermal performance. The torque constant is the simpler of the two. Brushless motors have a rating called the KT rating, and this basically tells us how efficient they are at turning power, or more specifically current, into torque. If you're familiar with the concept of a kV rating, the KT rating is the inverse of that. Since the KT rating is a measurement of torque divided by current, it's expressed in units of Newton meters per amp. And if we were to plot this relationship for any given motor, it would give us a linear relationship. On our test setup, we're going to measure how much torque each motor can output at a few different power levels to verify this number very precisely. And this is why the second concept is really important: thermal performance. The torque testing will give us a nice torque versus current line, but motors aren't perfectly efficient at converting power into torque. A lot of the energy we put into them gets converted into heat, and after a certain temperature that can cause permanent motor damage. The effects of heat on an object aren't super straightforward though. For example, even if we know the maximum amount of current we can put into the motor before it burns out, how do we know how long it'll take to get there? If we put less than the maximum amount of power into a motor, what temperature can we expect it to get to? Understanding these things will help a ton with designing the arm with confidence later on, by getting reasonably accurate estimates of performance without having to retest each unique setup. The main values we need to find with this thermal testing are each motor's thermal resistance and thermal capacitance. Thermal resistance tells us how effective an object is at dissipating heat, and thermal capacitance tells us how much energy it takes to raise an object's temperature. If that's too abstract, here's an analogy to make this a bit more tangible. Heat in an object behaves a lot like water in a container. Let's look at a bucket with a hole in it, where water comes in through a hose at the top and exits through the hole at the bottom. The water level here is equivalent to temperature in our motor. The water coming in from the hose is the same as energy flowing into the motor, and the water escaping through the hole is the same as heat being dissipated from the motor. Just like heat in the motor, there's a limit to how much water you can put in the bucket before it overflows. In a setup like this, as the water level rises, the water pressure in the bucket will increase, and water will flow faster out of the hole. When the water flowing in through the hose is equal to the water flowing out of the hole, the level will be steady. This is called equilibrium. If we increase the flow from the hose or decrease the size of the hole, that's going to cause the equilibrium water level to rise. In our motor, this means that if we either increase the power going into the motor, or if the motor is worse at dissipating heat, its steady state temperature will go up and be closer to getting damaged. To quantify these values when referring to heat, we can use thermal resistance and thermal capacitance that we mentioned earlier. Thermal resistance tells us how good an object is at dissipating heat. Lower resistance is better, and the units are degrees per watt. So if I put 10 watts into a motor with a thermal resistance of 5 degrees per watt, it'll settle at 50 degrees above room temperature. We can change the thermal resistance of a motor in a few different ways, one of which is pointing a fan at it to cool it faster. In our bucket analogy, that's like making the hole larger. And here's the key. With a bigger hole, we can either lower the equilibrium level with the same flow of water, or we could pour in more water while keeping the same water level as before. For our motor, better cooling means more power at the same safe temperature, and that means more continuous torque. Thermal capacitance tells us how much energy it takes to raise an object's temperature. If the thermal capacitance increases while keeping the input power and the thermal resistance the same, that means that it will take longer to reach the same steady state temperature. This is the same as having a larger bucket that has more volume, or more directly, a higher capacity. If the water from the hose is the same, and the hole is the same size, increasing the size of the bucket won't change the equilibrium water level, but it will increase how long it takes for the bucket to fill to that level. The thermal capacitance of a motor is going to be constant, but it will change from motor to motor. For this testing, I'm mainly focused on thermal resistance since that's what I can actually design around with cooling, but measuring the capacitance is going to give me valuable information for analysis. So that's what this test is about. I measured each motor's thermal resistance across 4 different cooling setups. No fan and no thermal paste, both fan and thermal paste, and variations of either one being absent, to figure out how much continuous torque I can actually rely on when designing the arm. Thermal paste is this gray substance that goes between the motor and the motor bracket and should increase how much heat is conducted into the structure. For the fan cooling, I used the same small PC fan for all 6 motors pointed diagonally towards the front of the windings. This is by no means optimal, but at least it was relatively consistent. With that out of the way, let's get to spinning some motors. I mounted the smallest motor to the test setup and then calibrated it. Calibration is just a sequence that the motor controller performs to figure out a bunch of values so I don't have to manually type them in. This calibration has to be done on every motor. Once that's done, we can start doing the important work. This is the torque calibration test setup. I've attached this lever arm to the motor so that when it rotates, it slowly presses on this load cell. The load cell is connected to a computer and reads very precisely the force that's being applied to it. With the force from the load cell and the length of the lever arm, we can calculate the torque being produced by the motor. And since the motor controller can read very precisely how much current it's sending to the motor, we can get a clear reading of each motor's torque constant in units of Newton meters per amp. I ran this test at 5 different power levels per motor and took the average of the results to confirm they were linear. Is that smoking? And that was indeed smoking. I got a little bit impatient trying to find the upper power limit for that motor, but thankfully it didn't actually end up causing any permanent damage, so I just went on with the rest of the tests. These were the final torque constant results. Feel free to pause if you want to look more closely. Next, it was time to perform thermal testing. The goal here was to turn all of the input power into heat while measuring the motor's temperature. To do this, I used a trick that's equivalent to applying the gas and the brake at the same time in a car. This meant that I didn't have to have some variable load that the motor was driving. It's possible to do this without even spinning the motor, but that would cause uneven heating, so I added a very slow rotation. This testing was done at 3 power levels per motor in the 4 cooling configurations for a total of 12 tests per motor. This gave us direct estimates of the motor's thermal resistance and thermal capacitance values that we looked at earlier with the bucket analogy. It's time to look at what every engineer is here for. Some data, some plots, and some conclusions. I won't go over every single plot because there's about 200 of them and about 20 Excel sheets, but I'll go over some of the important ones. For the thermal tests, I had to get very accurate temperature readings of the motor windings because that's where all the power turns into heat. So for each motor, I wedged a tiny temperature sensor in the windings with some thermal paste to guarantee the best results. For each of the 12 tests on a given motor, I got a plot like this. From the temperature data, I could extract what the ambient temperature was at and the steady state temperature of the windings. And I was able to fit a model to this data to extract the motor's thermal resistance, thermal capacitance, and the thermal time constant. After all 3 power level tests for a single configuration, I plotted them in a single figure and averaged them to make sure that things looked relatively consistent. And after all 12 runs for each motor, I got the most useful plots of all. First, I got this thermal response plot. To generate this, my script first calculates the maximum power for each motor that results in a 75-degree steady state temperature, when no cooling is used. That's the upper temperature bound I use for all the motors. Then it calculates at the same power level how much cooler it would be for the other cooling configurations. For example, here we can see that for this motor with no cooling at all, the maximum continuous power is 18.2 watts, and that would cause the motor to get to 75 degrees after about 25 to 30 minutes. At that same power level, just by adding thermal paste and a fan, we get a 47-degree steady state temperature. The next plot translates this cooling improvement directly into a torque figure. So in the case of the motor from the last plot, the addition of the fan and paste increased its torque output by 50%. That's a huge improvement. Next, there's a heat map grid of all configurations for all motors based on how much torque they generated. This just makes it easier to compare all the motors in one place. Here I've plotted the torque per dollar for every configuration. This divides the total torque generated in that configuration versus the cost, accounting for a few dollars for the fan and the thermal paste. This shows that especially for the larger motors, it makes a lot of financial sense to implement cooling. And this was with a pretty small fan. I'd expect this to get even more significant with a larger fan. And here's the cooling effectiveness comparison. It's worth noting that for nearly all motors, the combination of the fan and thermal paste was more effective than the sum of the addition of just the fan or just the paste. If that was too technical and I lost you there for a bit, if you remember one thing from this video, it's that adding really basic fan cooling increases the steady state torque output of these motors by about 20 to 40%. And adding a fan and some thermal paste increases that number to about 25 to 45%. So what does all of that mean for a robot arm? For one, fan cooling is going to be absolutely critical, especially for the first few joints that are going to see the highest loads. Thermal paste is also useful, but not quite as critical as fan cooling, and it can be a little bit of a logistical problem because it's a little bit messy, so we'll use that when we can. The specific numbers that we calculated this video are going to be super useful next video when we're going to look at the mass of each robot joint and overall torque budget for the robot arm. I made the mechanical test setup to make sure that everything was consistent physically, and I also made an entire software testing suite to make sure that all of the data was being processed the same way, and all of the results were being generated automatically. If you want to take a look at the test jig CAD, any of the software, or the rest of the plots, head over to the new Vertex Robotics website that's linked in the description. Next video is going to cover actuator design and testing. If you learned anything or you want to follow the project, think about subscribing. See you in a few weeks.